All right, good morning, everybody. Happy Halloween. Yeah, I threw a picture of our family trick-or-treating last weekend because um, our town did it on Saturday of last weekend versus today, which I thought Saturday was cold, but I'm glad that it's actually not today because I heard, rumor has it, it's not even supposed to get above freezing today. Brr. I know, it's kind of like take your breath away cold at the start of the season here. Yeah, our dog was supposed to be Dry Bones. I don't know how many of you are familiar with Super Mario. I have a better picture of her. Let's see if I can find it. Here we go. She's actually wearing like a skeleton bandana. It just didn't come across in the picture very well. She doesn't pose for pictures too great when there's a lot of people around. But she was cute, right? All right, on to kind of some more important things other than trick or treating. I'm not sure what could be more important than candy, though. But you guys are probably sick of hearing me talk about the November 5th deadline. November 5th is this week Sunday, so make sure you have everything up to and including the 3.04 assignment turned in by that deadline. Obviously, we're talking about 3.04 today. And we'll be talking about um, 3.05 on Thursday, but I don't think 3.05 technically has to be turned in until next week, Monday. So that one doesn't make the deadline cutoff. Just the 3.04 does. Are there any questions with that deadline or anything like that? Mostly everybody in here is fine. Just make sure you take a peek at your grade book and you have no zeros entered for missing assignments. So just take a peek at it before the end of the week, but most of you are fine in here. All right, if there are no questions, then we're going to jump right into 3.04. Remember, we're talking about logarithmic functions. So today we are reviewing some of the properties that we learned back in Algebra 2 with those logarithmic functions, and we're going to expand on that a little bit here today in pre-calc. All right, so as a review, there are three properties that we're going to look at. We can use these properties to expand or condense logarithmic equations. Okay, so the first property we have is the product rule. And the product rule says that you can, as long as you have the same base, all right, so really important, whether that's log with base b or natural log with base e, you must have the same base before you can expand or condense something. Right? If they do have the same base, you can expand or condense your multiplication using addition or the other way around. Right? So if we want to expand log base b of r times s, we can break that up into log base b of r plus log base b of s. Now notice it does go the other way around as well. So if you're given the addition rule here, you can condense it into multiplication. So notice that they keep that log with the base that they have in common, and they're going to be multiplying the r and s together. The quotient rule is probably just what you would think. If multiplication means addition, then division is going to lead to subtraction. So again, you must have the same base, and if you do, you can split up r divided by s by using log base b of r minus log base b of s. And this does work the other way around as well. So you can condense it if you have subtraction by dividing r and s. And the last one is the power rule. We actually saw this being put to use when we were solving in the 3.03 2 lesson, I want to say last week when we were doing 3.02, we were able to bring that exponent down in front once we did the log of both sides, right? That's because of the power rule. So the power rule allows you to bring that exponent out in front of the log. Okay, so give you a moment, copy those down if you need them as a refresher. Let's go ahead and take a look at them being put to use then. All right, so it says, assuming x and y are positive, use the properties of logarithm to write the log of 8xy to the fourth as a sum of logs or multiple of logarithms. All right, now we don't necessarily need it here, but I just want to reiterate, if there's no base that's written, what base are they assuming is being used? Good, base 10. So I just want to point that out. If you're using log and no base is written, it's your common log of base 10. Now down here, when they're using natural log, what's the base of natural log? So if nothing is written there, which it shouldn't, E is the base of the natural log. Good. So again, not really important for this problem whatsoever, but I wanted to review those common bases so that we know what we're looking for later on if it ever comes up. All right, so let's go ahead back here to example 2 and let's expand this. So let's start with log base 10 of 8. So log of 8. I'll have log of x and log of y to the fourth. All right, what operations can I use to connect these three things? So all I did was take what was inside parentheses and put log in front of each one. Because we're using multiplication, we can connect them with addition. All right, we're not quite done yet. What else can be done? You can rewrite 8. Yeah, so that's not really like the first thing that comes to mind, but you definitely can rewrite 8 as 2 cubed. Doing so is actually going to lead to an additional step. The one thing that I noticed first is the one that Tommy picked out, and that's the 4 as an exponent. We can use that power rule to bring it out in front. And now speaking of the power rule, because Rebecca rewrote 8 as 2 cubed, we can use the power rule here as well. And that power rule says the 3 can come out in front. If you don't notice this first one and that 8 can be rewritten as 2 cubed, that's okay. I would still accept log of 8. But I do expect this last term, the 4, to come out in front, because that is given as an exponent, so we know that that should definitely be written out front. Okay, so if you have log of 8 plus log of x plus 4 times log of y, I would have accepted that as a final answer for expanding that. All right, how about the next one? All right, I noticed that we're using natural log. It still has the same properties as your logarithms do. So let's go ahead and try to split this up. Any ideas how I can try to split this up? All right, let's see what we got here. The natural log of, and I like that you have the square root of x squared plus 5 inside parentheses here. And you did use subtraction to break up the division. I'm going to do an extra step. I'm going to put just an x squared plus 5 inside parentheses here. If I write this as the natural log of x squared plus 5, what would be the exponent on that? The 1/2, because I'm missing the square root from it, right? So notice the square root is missing. I have to express that as an exponent. And the exponent for a square root is to the 1/2 power. So we want to go ahead and write a 1/2 out there. All right, there's only technically one rule that's left to rewrite this in expanded form. What's the last thing that we can do now that we have it written like this? The power rule with the 1/2. Yep, so we're going to bring the 1/2 out front, and you'll have the natural log of x squared plus 5 minus the natural log of x. Now, can I split up that x squared plus 5 that's inside parentheses? No, we cannot. We cannot split that up at all. The only way we could split it up is if multiplication was being used here. Good. All right, any questions with expanding using the properties of your logarithms? Okay, then let's see if we can go the other way around. We're given the natural log of x to the 5th minus 2 times the natural log of xy. It says to rewrite this as a single logarithm. All right, so how are we going to do that? How can we write this as a single logarithm? Division. Yeah, before we do division though, I want to take care of something else. What do I want to take care of before the division? Yeah, we want to take care of the power rule. So we're going to go ahead and technically you can still get the right answer if you were to use division first. But I am going to throw this up as an exponent. Notice how the exponent is being put on the outside of that parentheses. So that means that that 2 can be applied to both the x and the y. All right, so notice how it's on the outside of those parentheses. So using division, we'll do x to the 5th over xy squared. And I'm going to go ahead and actually get rid of the parentheses in that denominator. And the purpose for that is because I can actually simplify what I have inside here. So notice that's an x squared y squared. How is that going to simplify? Yeah, notice that you can take x to the 5th over x squared, and you would subtract those exponents to get x cubed. So the natural log of x cubed over y squared is going to be our final answer. Awesome. Questions with how we condensed that? So kind of working backwards now using those properties. Okay, I saw his eyes typing, so I didn't want to go too fast, but it disappeared. So hopefully we're all good. All right, we got 8 questions here. It says 4 of them are true and 4 of them are false. I'll give you a little bit of time to put T or F after the problem. So take a look at what they have on the left-hand side and what they have on the right-hand side. Do the two things equal each other? Oh, well, you can throw it in the chat box anyways. So while we're working on this, if you want to throw it in the chat box, feel free to do so. But I'll give you guys a few minutes here to look at those 8 questions and mark either a T or an F after them if the statement is true or if the statement is false using our properties. Oh, okay. All right, that's a good question, guys. When we're done with this one, we'll go back and take a look at that. All right, I'm just going to go through and take a look at the answers that you guys were putting on the board here. I'll highlight the ones that I agree with. All right, I think we need to swap the answers for 5 and 8. When I take a look at this, what do I actually want to use? What operation should I use in question 5 to separate the division problem? We actually want to use subtraction. Yeah, so this one is going to be false because we would rather see it as log of x minus log of 4. So that would be the correct separation, which means 8 has got to be true then because you need 4 true and 4 false. So we would then go ahead and add log of 4 plus log of absolute value of x. I don't believe they actually would equal each other still, and this is kind of what Isaias was alluding to with the last question as well. If I put any number here, like a 2, let's check it out. So we'll do log of 2 over 4, which is just log of 1/2. So real quickly, using our calculator, what do we get when we take log of 1/2? What's the decimal? Do you get negative 0.301-ish? Okay, now let's check it out. Let's do log of 2 divided by log of 4. I'm not sure if they're actually going to be the same. And they're not. So when I take a look at that, we get 0.5. So we notice that we can't just put log with that division problem and separate those. We have to use the subtraction here. Let's check it out now using the subtraction though. Does log of 2 minus log of 4 equal the negative 0.301 we had before? Let's check it out using the subtraction now. It does. Awesome. So that's just a quick algebraic thing we can do to show that that property with the subtraction is going to work out, where separating using a division sign will not. So great question, which leads back to what Isaias was saying back here. He's saying, are these actually the same? Would I get the same output if I started with an x and a y value and I substituted those in the end here? Is that kind of what you were asking, Isaias? Are those really truly the same value? Can we test it out, that type of thing? Right, which means the original could have been simplified even more. So I did break it apart. So this natural log of x cubed divided by y squared, if I were to break that apart using our properties again to expand it, this is what we get. It was not the exact same thing as what we started with. So are these actually equal to each other? Well, let's choose some values for x and y. Let's have x equal, let's just do something basic, right? X equals 2 and maybe y equals 3. I don't know, we'll just do something like that. I want to stay away from 1 because the natural log of 1 is 0. So when I'm substituting values in, we'd probably want to stay away from the value of 1, only because when we're working natural log of 1, that reduces to a 0. We have that property way back in Algebra 2. It'll be brought up again, I think, in the future as we continue working through things. But note that the natural log of 1 simplifies to just a 0. So to avoid that, let's just use the numbers 2 and 3. All right, I'm going to just plug these into my calculator and see what we get here. And I don't know if you guys want to take one thing and I'll try the other. So if someone wants to maybe start with this one and plug in the values of 2 and 3, and I can take the end and plug in the values there, and we'll see if we get the same answer. All right, did you get a negative 0.11778? Yay, me too. And I actually did both of them. So I did that natural log of 2 to the 5th minus 2 times natural log of 2 times 3 in there. Awesome. So they are the same thing. It's just that this one, we did simplify along the way to get this answer. So technically this is like a reduced form of what we started with. So think of it as like your fractions. 4 over 8 is the same as 1 over 2. That same idea is being applied here with your natural logs. So we started with a form that wasn't necessarily reduced all the way, but our answer was. So they're still equivalent because they still equal the same thing. It's just what we started with wasn't necessarily reduced as like what we had in the very end. So try to relate it back to something we can understand and see what's going on there. So good. Any other questions with those? So lots of good questions coming up with these properties. Okay, the other thing we have to address is our change of base formula. The change of base formula allows us to evaluate any logarithm. So any logarithm, no matter what the base is. Your calculator, unfortunately, only calculates things in base 10. And the problems that we look at are not always base 10. So we can use the change of base formula to figure out what that value actually is, what the numerical value is. So the change of base formula says that you would take log of whatever this value is out here, so log of 16, and then divide that by log of whatever the base is. So as you're writing this, always keep in mind that the base goes in the denominator. Okay. Now, as I'm writing this out, you can technically use any base you would like. I am obviously using base 10 with my formula because that's what my calculator does. But you can, for some odd reason, use any base you want when you're using the change of base formula. Okay, obviously we want to use base 10 because that's what the calculator does. So plugging that into the calculator, what decimal does that equal? Or what number? We probably will have to do some rounding with these. Yep, I would round to the nearest hundredth or thousandth. And the thousandths is probably the better of the two because it's a little bit more accurate. All right, go ahead and do parts B and C as well. So when you have that decimal answer, throw it on the board behind parts B and C. All right, awesome. The little note down here is just stating that your change of base formula works with logs or natural log. So technically I use logs up here. You can also use natural logs to split those up. I just did the first part A and B there to show you. You get the exact same decimal answers when you use the natural log versus the logarithmic function in the calculator. So change of base formula works either way, log or natural log. Okay, we can actually use our change of base formula to see what type of transformations are occurring with our graphs as well. So remember in our previous units we were talking about how a graph can be transformed. So shifting it left, right, up, down, reflecting it like over the x-axis or the y-axis, stretching it or shrinking it. The same thing can be done with your logarithmic functions. However, you have to use the change of base to see what's happening to the graph. So it says, describe how to transform your graph of natural log x into the functions that are given here. So we're going to start, and we want to change this to the change of base formula. So that, and because we're comparing it to natural log, as I separate the things, I'm going to do natural log of x over the natural log of 5. Because on the last slide, I just told you that you can use log or natural log with that change of base formula. They mean that they equate to the exact same thing. All right, I'm going to do something crazy here. I'm going to rewrite the problem as 1 over the natural log of 5 times the natural log of x. So technically all I did was take this numerator and put it next to that fraction of 1 over natural log of 5. Doing that allows me to see what type of transformation is actually occurring to my graph. So if I'm multiplying, because this is just a constant, right? So if I'm multiplying a constant by that function, what type of transformation is happening? So if you're multiplying a constant by the entire function, what type of transformation was that? That was a vertical stretch. Yeah, so technically what's happening to the graph here is a vertical stretch by a factor of 1 over the natural log of 5. Okay, not too bad, right? Now, it took a while to actually understand what was going on there and how we use the change of base formula to rewrite that function. But any questions with that first one? Okay, let's do the same idea with part B. So part B, let's start with your change of base formula. So that would be your natural log of x over the natural log of 1/4. Now, this is a little bit crazy, but can I split up the natural log of 1/4? It is a fraction after all, which is a division thing. Can I split that up in the denominator? What can I use to split that up? You're right, we can. What can we use to split that up? The quotient rule, yeah, so that means you have to subtract the natural log of 1 minus the natural log of 4. Because it is a fraction after all, division problem. That's what a fraction bar means, so you can break that up. I just got done telling you what the natural log of 1 was, but type it into your calculator to verify. What is going to be the natural log of 1? So we can simplify that. What's the natural log of 1? It's just 0. So technically, you have 0 minus the natural log of 4. Well, that minus sign can be brought out front. You now have enough information to see what transformations are occurring. And there are 2 transformations that are occurring. What are the transformations that are occurring? And if you only see one of them, tell me the one that you see. There is a reflection over the x-axis. Yep, and it's a reflection over the x-axis because the negative sign is out in front of the entire function. And then there's also a vertical stretch. Very good. Vertical stretch by a factor of 1 over the natural log of 4. Perfect. So that natural log of 4 in the denominator should have reminded us of part A with the vertical stretch there. But that negative sign should also prompt the reflection across the x-axis. So 2 different transformations occurring there. Questions with the part B? All right, nice job, because that one was a tough one. It's hard to see the transformation sometimes with the logarithmic functions. All right, we've gotten to the point of class where we can just start practicing what we've learned with our properties. So pick a problem or 2 to expand using your sum or difference of logarithms or that power rule as well. So pick one of these and expand it out using your properties. So we want to expand that using the 3 properties we talked about here. Once I see the answers start to populate on the board, obviously I'll go through those and verify that they are correct. All right, first one looks good. You separate that using addition. The second one you separate using subtraction. I love how you only put the 3 in front of the y. Perfect. Notice the 3 is only attached to the y variable, not the x. Therefore, a 3 does not belong in front of the log x. Very good with this one here. This one looks good. And sometimes when we're typing this out, when it has a base like log of 2, you can go ahead and put like parentheses around that x if you'd like. That just lets me know that the 2 is technically that subscript. It's the base of the problem. And then the x is not in the base anymore. So if you want to add parentheses as you type that out to separate kind of the log, you can do that. I'm taking a look at the other answer that popped up for the third question here. You could also write that as log base 2 of 1 over x squared. If you do that, you would do log base 2 of 1 minus log base 2 of x squared. I ran out of room, which is log base 2 of 1 minus 2 log base 2 of x. So very similar, but it's still different if we were to separate it that way. You can do it. It is the exact same. You most definitely can. And let me just take a look at the last one. Log base 10 of 1,000 plus 4 log of x. Looks good. We can technically reduce this log of 1,000 because it is base 10 here. What is log base 10 of 1,000? It's 10 cubed, right? So technically, if we remember all of our properties, right, the log base 10 of 10, those cancel out, so you just have the 3. Good. So 3 plus 4, and I forgot my last one over here, of log x. That looks good. Good. Very good. Any questions with those? So again, some of these have multiple representations when we expand them. Ooh, here's a toughie. All right, I'll give you a little bit of time to think about how we can expand this one. And don't think too hard, because it's actually not too bad. Yeah, let's throw that on the board. So natural log of x to the 1/3 minus natural log of y to the 1/3. Good first step. And then Tommy just brought those down. Well, she brought one down, but not the other. I'm going to do both of them. Use the power rule for both of them. So natural log 1/3 times natural log of x minus 1/3 times natural log of y. Good. I think the hardest part was just knowing that that can be written as x to the 1/3 power and y to the 1/3 power. If you wanted to, another way you could do that is you could factor out the 1/3. So that is another way to express your answer. Right? She had to outdo you just a little bit, but didn't want to go all the way with it. All right. All right, let's go ahead. There are 5 more up here on the board. Let's condense them this time. So if they have the same base, remember you can only condense things that have the same base. So if they have the same base, go ahead and condense that as far as you can. When I see the answers pop up, I'll go ahead and box them just to let you know that they are correct. Yeah, make sure in the second problem that you are not putting the natural log of x divided by the natural log of y. That's not the same thing, so just make sure you're doing x divided by y and taking the natural log out in front of that. Ooh, the 5th root of x. I like it. You could also do x to the 1/5 power for this last one. So another way to write that would be log base z to the 1/5 power, but this is the 5th root of z, so that also works. Yep, in the bottom row, which we're starting to get a little bit more challenging problems there, don't forget the log that's out in front of the y to the 4th divided by z. It's a good idea to put parentheses around that y to the 4th divided by z as well. There you go. And then the last one, I like how we brought up the powers here. So 3 and 2. Let's actually simplify these. Because we can simplify these, I notice they have y's in both set of parentheses. So we'll want to combine those to reduce that if we can. So let's distribute the 3. When I distribute this 3, should I be multiplying my exponents together or do I need to add them? What's the rule with your exponents? Not add. We're going to multiply. So this one is actually going to be natural log of x to the 9th y cubed and then y squared z to the 4th. So if you just have a parentheses that separates the exponents, that's when you multiply. Now notice I now have bases that separate my exponents. I have y cubed times y squared. So as I'm multiplying those, I add my bases together now because they have a whole base that separates the exponents. So we can still take this a step further and we can say this is x to the 9th times y to the 5th times z to the 4th. Okay, so we kind of went way back with our exponent rules to our Algebra 1 days, believe it or not. Questions with that? Why does math is upon it? Right, I know. Why was the 4 exponent on the outside? I don't see where it is on the outside because it's here and here. So I don't actually think it's on the outside anywhere. Like, why did I put z to the fourth at the end? Is that the question? In the So up here? I guess I'm lost on where you're at. So following through this first equation here, the 3 and the 2 must be brought up as powers. So let's walk through the whole problem and hopefully that'll clear things up. So this and this must be brought up as exponents. So we have parentheses that those need to be applied to. So notice we go from step 1 to step 2. So everything is the same except that the 3 and the 2 are now written as exponents instead of out front because that's using our power rule. Now we have to use our rules of exponents. So if there is a parenthesis that separates your exponents, you must multiply the exponents together. So this turns into 3 times 3, which gives you x to the 9th. And then 1 times 3 to give you y cubed. Over here, same thing, but we have a new set of parentheses. So this is going to be 1 times 2 to give you y squared, and 2 times 2 to give you z to the 4th. Now, technically, we are multiplying these two parentheses together, but notice now that we have a base that separates my like terms. So the only thing I have left to kind of combine, so to speak, are the y's at this point. So y cubed times y squared is going to give me the y to the 5th in the middle. So I just multiplied these two things together to get x to the 9th, y to the 5th, and z to the 4th inside the parentheses. Hopefully that helps a little bit going through it step by step. Okay, great. The last thing real quick before you leave is let's just figure out what these decimals answers are. Notice these are not base 10, so you need to use your change of base formula to figure these out. So go ahead, grab those calculators and use your change of base formula to get the numerical value for each of these logarithms. First one looks good, 1.829-ish. Last one looks good, negative 2.092. Middle one looks good, 2.236. Perfect. So that is real quick. Punching in the calculator is the only way we can get those options or those answers. All right, that's it then. Any questions regarding lesson 3.04 with those properties of logarithms?